Okay, welcome back. The second lecture today is about the evidence for tunnel ionization and the introduction to the Wkb method. We quickly recapitulate what we were just talking about, namely the different this overview of ionization mechanisms and the introduction of the Keldysh parameter in order to distinguish whether we should talk about a multiphoton ionization or tunnel ionization. Is did you have any questions about this? If this is not the case, we'll just continue from there. Yeah, so the main point, well, actually one remark. So in the script you will find a section entitled Theoretical Limits. We will skip this now for reasons of time limitations, but maybe we can discuss it in the seminar, which takes place right after the lecture. And the Zoom session will also be recorded this time, and then we will make it available on Moodle afterwards. Okay, now we'll continue with section 3.3, the experimental evidence for tunnel ionization. And, oh, the projector is off. Ah, there it is. Ah, it's always off. I see. It's okay. It's off when the camera shows me. Okay. Yeah. So we'll continue with 3.3, experimental evidence for tunnel ionization. Yeah, so as a quick lesson from the previous section, we found that in order to achieve gamma smaller than 1, or significantly smaller than 1, we want to go to long wavelengths. And this is in line with our previous discussion that if you have a static field, then you have this nice tunnel scenario, which is very similar to the case of tunneling microscopy also. Yeah, so here is again the definition for around 1. You Okay, das zeigt leider jetzt auch hier nur, es zeigt nicht einen Balken, es zeigt gleich Low Battery. Haben wir da drüben noch andere? Na, der hat, nee, der hat auch keine Balken mehr. Ja, vielleicht finden wir es so, dass wir zumindest jetzt noch der hat auch keinen Balken mehr. Na, der hat zumindest noch einen Balken. Okay, once again, apologies. I think we learned our lesson. We should always restock on batteries here. Okay, yeah, so the main conclusion is there are strong, so strong violation of perturbative behavior from this experiment. Yeah, so this shows that tunnel ionization is really strongly different. Yeah, it requires different methods to calculate than a multiphoton ionization where you would use perturbation theory. Okay, can we switch back to the iPad, please? Where did I, here. Okay, so conclusion or finding here. I think we should draw this to have at least a little sketch. Yeah, so plotted here is the logarithm of the intensity and here the logarithm of the ion yield for different species. And what is found is that we have here xenon plus, xenon 2 plus, xenon 3 plus. And these lines, they are essentially parallel to each other. Yeah? Even though, as discussed, one would expect that these here are much steeper than this one. Yeah? And this one should be steeper than that one. So the finding, point 4, xenon n plus ion yield increases as approximately intensity to the 10th power. And that is independent of, for one thing, the wavelength. Yeah, so whether you use 9.5 or 10.5, with the 10.5 again, you would expect a steeper increase because of the larger number of photons involved. Yes, independent of lambda, and what's even more surprising, of the charge state. And this means it's independent of the ionization potential. And this violates the expectation for multiphoton ionization, where we expect that the yield scales as intensity to the nth power where this is the number of photons required for ionization. Yeah, and so the conclusion is that multiphoton ionization is really not the right picture, and tunnel ionization is very different, or scales very differently. So MPI is not useful here. Tunnel ionization scales differently. Okay, one point that we should make with respect to our barrier suppression intensity is that, can we show the presentation in addition to the iPad? Yeah, so one remark that we should, oops, did I just lose connection? No. Okay, let's just go back to the iPad. This doesn't seem to work right now. Okay, so one remark that we should make is that the intensity actually, the total intensity actually approaches the value of the barrier suppression intensity. Yeah, so this is roughly somewhere here is 10 to the 14 watts per square centimeter. 10 to the 14. And but here, yeah, so where the xenon plus starts to saturate was actually only 10 to the 13 watts per square centimeter. And that's of course much lower than the barrier suppression, yeah? So the maximum intensity seen by xenon plus, yeah? So basically if you exceed this value here, or maybe that value, yes? So there's a certain value at which basically all the xenon atoms, all the neutral xenon atoms have been completely ionized. Yeah? And so the neutral xenon atoms will never even experience this high intensity of 10 to the 14 watts per square centimeter. Yeah? So the maximum intensity seen by neutral argon is approximately, did I see? Oh, argon. Ah, xenon, yes, thank you. Is approximately 3 times 10 to the 13 watts per square centimeter, which is significantly below the barrier suppression intensity. Yeah? And only above that, above that higher charge states are produced. And so we shouldn't calculate gamma for the peak intensity, but rather for the for this intensity, where the atoms are ionized. Yeah, and there we have UP equals 300 electron volts roughly, and from this it follows that gamma equals 0.14, which is still much smaller than 1. Yeah. And so these pretty much ideal conditions for tunnel ionization, they have remained unmatched. These ideal conditions for tunnel ionization have okay. Now, so this experimental evidence now motivates us to develop an approach how we can calculate the tunnel ionization probability. And for that, we use the so-called Wkb approach, which is named after the physicists Wenzel, Kramers, and Briand, who independently developed this method in 1926. So this is here the Wkb approach. Yes, that's right. So we'll actually so we'll actually solve the Schrödinger equation to calculate a tunnel probability. No, here not. For the tunnel probability, we'll use quantum mechanical calculations. Yeah, but then we put this rate that we get from there into our classical model, which is why sometimes this classical model is referred to as a semi-classical model. I mean, it's one reason. You can also put quantum mechanics into the propagation, by assigning a phase to the electrons that are now so far completely classical. Okay. So our goal is deduce the tunnel ionization probability as a function of the electric field strength. So T of E. And we do this in 1D, and we'll use the Wkb approximation. So we'll first consider a particle with a fixed energy E in a constant potential, yes? Pretty much as we have done above here. Here we did this. Yeah, for to get an expression for the kinetic energy there. So consider a particle with energy E in a constant potential V. And then for E over V, E larger than V, the solution, or let's say the wave function, is or can be expressed as so this is the solution to the time-independent Schrödinger equation. Yes, this can be expressed as something like this. Yes, so you have an amplitude and an oscillating term, and the particle can move from the left to the right or the right from the left. That would be in this in the sign here, plus or minus. And K would then be given by 2m E minus V over h bar. And the square root actually ends here. Yeah, and for so if the energy is larger than the potential, so we're not in the classically forbidden region, E is larger than V. And so the particle is oscillating. Yeah, this is because K, the wave vector, if you think of a light wave, this would be the wave vector, is real. And the wavelength is, of course, 2 pi over K. And the amplitude is constant because the potential is constant, yes? Okay, and now the idea is if the potential is actually not constant, but slowly varying, then the solution should remain in the same form. Only these parameters A and K, they would now depend on space. Yeah. If v of x is slowly varying, then the solution should remain or keep, let's say, then the solution should keep its general form, but A becomes dependent on x, and so does K. Yeah? This is the central idea. The question is only what means slowly varying. Yeah, the answer would be that it doesn't really, that the potential doesn't really change on the length scale of the wavelength that the particle has. Yeah. V of x is essentially constant. On the scale of lambda. Yeah, so v of x is roughly the same as v of x plus lambda. And yeah, so this has the advantage that you can actually just slowly change the parameters as the wave propagates, and you can solve such problems. Okay. However, what we're interested in is the tunneling region. This works analogously in the tunneling region. Here, however, yeah, because now E minus V becomes a E minus V is actually smaller than 0, so this will become negative, and then this means K becomes complex. Here, however, K, it's not a euro, it's an element. K is a complex number, and then we'll actually use kappa instead. Not happy with this kappa. Yeah, this is now actually I times K, and this would be 2m V minus E over H bar, where this is now larger than 1, larger than 0, yeah, because we exchanged V and E there. And then the wave function would be exponentially decaying. So note that I'm writing minus plus instead of plus minus. And analogously to above, if we now have a changing potential, then kappa would depend on the position, and well, the amplitude would anyway depend on the position because of the exponential decay of the wave function. What we should note, however, is the limitation, and this is of course the condition that we applied, namely that the potential must be slowly varying. So when E minus V approaches 0, yes, then the wavelength goes to infinity, and then it's no longer possible to speak of slowly varying. Yeah, so this means actually at the entrance and at the exit of the tunnel, these are the problematic regions. Okay, and we'll take a closer look at this first for the classically allowed, then for the classically forbidden region next week. Thank you so far for the attention, and see you in the seminar in 25 minutes or so. No, 20 minutes. Thank you.